Let's see how to calculate a vacancy formation energy in SEAMM using LAMMPS and a force field. This is a picture of a number of defects in a crystal. The one we're interested in is the vacancy at the bottom left where an atom has been removed. There's a slight trick to this. The atom is not moved into vacuum, it's moved somewhere else in the crystal. So we will simulate a crystal with n atoms and then a vacancy system with n-1 atoms, do a little math to get the right answer. It's a constant volume process. When you take an atom out, put it somewhere else in the infinite crystal, the size of the crystal doesn't change. So the protocol we need is we need to choose the potential or force field for our simulations. Need to create a large enough perfect crystal, calculate its equilibrium volume or density, calculate the energy of the crystal at this equilibrium volume, remove one atom, calculate the energy at the same volume, and then evaluate the equation to get the vacancy formation energy. Really quite simple. Here we are in SEAMM, ready to turn that protocol into a flowchart. First, we need to select the force field. We can use OpenKim, select on the element we want. Aluminum is the system we're going to work with. And down here we get a goodly number of potentials out of the OpenKim project, but we'll just take the default one. That's fine to get us going. Is to build a large enough piece of the crystal, large enough so the defect doesn't interact with images of itself. So we get the crystal builder and set that what we want to do. We want to build an FCC because aluminum is an FCC cell, change the lattice parameter to be something about the right size, and put in aluminum as the element and say OK. Since the FCC crystal only has 4 atoms in it, we need to make it larger, so let's make a supercell. It needs to be larger, not only so they don't interact with each other, the defects, but also so temperature and other properties, which are bulk properties, are well defined. We'll just make a 5 by 5 by 5 unit cell. That's good enough. We have the system. We need to calculate the equilibrium density, so we will use LAMMPS and run NPT dynamics. So that's constant pressure, constant temperature dynamics, which will give us the equilibrium structure at this temperature. First, we need to initialize, basically set cutoffs and other things, which the defaults will be just fine. LAMMPS wants you to set the velocities, which we will do. It'll run at room temperature. That's a good place to start. And now we run NPT dynamics. And we will ask it to run for a fixed length of time and keep it fairly short because this is a quick demo and the system equilibrates quickly. So everything else can be left the same, temperature and so forth. So now we are able, forgot one thing, we need to save the density at the end of this so that we can set the cell to the average density that's been calculated. And I'm just going to call it rho, set it in a variable. Now, once that's run, we've got the density. We need to set the volume of the cell to that equilibrium volume that was just calculated. To do that, we use the set cell step, and we're going to adjust the cell by the density and use the variable we just created, rho, with a $sign in front of it to indicate it's a variable. So that will set the volume to the average volume that we had. Now we need to calculate the energy of the perfect crystal at our temperature at this volume. So again, we run LAMMPS, do the initialization, that's fine. Set the velocities, and now run NVT dynamics. And again, we're just going to set it to run for a short length of time that will be sufficient for this system. And we don't have to worry about anything else, just to keep this nice and quick. We do need to save the results. So this time what we want from it is the potential energy. The total energy includes the kinetic energy. That's not what we want. We want the potential energy. And we're going to call it En for the system with n atoms. Okay, that does that. Now, after that simulation finishes, we need to remove one atom. We don't have a step to actually do that, But what we can do is just add some custom Python code to remove one atom. We're also going to need the number of atoms later for our equation, so let's capture that now with a simple expression. System is the molecular system that we're working on. Ask for the number of atoms and save it in a variable called n. So we can save that. Oh, yes, before we do anything else, we forgot to remove the atom. So let's edit again. You can always go back and change your work. And then we will just type in the command to remove one atom. This crystal is, all the atoms are the same, so it doesn't matter which one. We'll just remove the first atom just for simplicity's sake. So that's created the system with a defect in it. We now have n-1 atoms, and we're back to calculating the energy, again using NVT dynamics, constant volume dynamics. So we initialize, we've set the velocities, we run NVT dynamics, and again set this to just to run for a short length of time. For this simple system, it equilibrates very rapidly, and we need to save the energy, so we go down and find the potential energy, and this time we will save it as En1 for n-1, the system that we're looking at with n-1 atoms. Okay, now finally we need to calculate the vacancy formation energy with the equation we saw earlier. So again, we go back into some custom Python and just type that equation in. We've saved the variables, so the vacancy energy is the energy of the system with one atom removed, minus n-1 over n times the energy of the system, perfect crystal system. So we just type that equation in. I'm pretty bad at typing. And then we need to print that out so we can see it. And we use a special command called printer here instead of just plain print, because it may be going several places. So we just print out the result. Okay, that concludes building the system. Now we need to run it. As we've seen before, we can select the machine to run on. I'm going to put it in development again just so I don't clutter myself up, and give it a title. That has started it running. We go over to the dashboard again in the browser and update our list of jobs, and there is the job that we just submitted. It's running. It's going to take a little while, so I'm just going to break here and come back when the job is finished. Okay, now the job has finished. We can again look at the structure, for instance. This is a little more complicated than we had before, so that will be the defect structure. It's actually the last structure that was there. Here's the output with the long section at the beginning telling us what it was going to do. That's so if we're running a long calculation, we can check and make sure we're actually doing what we wanted to do. Now here it is running the flow chart, creating the system, running LAMMPS, giving a statistical analysis, setting the volume and so forth, and it just keeps going and doing all these steps, and then at the end there's what we printed out. The vacancy formation energy is about 0.85 EV. And finally, we have the list of references for these calculations for all the tools that have been used. Okay, to wrap this up, we spent a few minutes developing a flowchart which we ran. Calculated the vacancy formation energy and got about 0.85 EV for aluminum. And as you can see from this paper, the experimental value is just under 0.7. So we have a reasonable result. But of course, we need to explore whether the cell was large enough, which we could readily do by changing the number of copies of the cell that we duplicate, and we may need to test some other things, but that's easy to do by changing this flow chart and playing around and seeing what the real result should be.